Okay, I think we'll get started. So today we're going to talk about the composition of Blaschke products with Möbius transformations. So we're going to look at the Blaschke product of a Möbius transformation of Z, and then we're going to look at the Möbius transformation of a Blaschke product of Z. This is going to be important for a variety of manipulations of Blaschke products, but most immediate to us is the next lecture. We're going to normalize the Blaschke product, which in doing so, we take a Möbius transformation that takes one of the zeros to z equals 0, and then it does a Möbius transformation that rotates the Blaschke product so that the value of at z equals 1, the Blaschke product of 1 is equal to 1. So in order to do that, we need to compose with Möbius transformations. Now, the Möbius transformation set that we're interested in are the automorphisms of the disk. So those are the ones that are going to take the interior of the disk to the interior disk, and the edge of the disk, or the unit circle, to the unit circle. And they are of this form. There's the form of a rotation and what's called an involution. And so this is such that the rotation is given to us by e to the I lambda, where lambda is a real number between 0 and 2 pi. And then a is a complex number from the complex unit disk. All right, so we're going to do first the composition where we do a Möbius transformation of Z and then the Blaschke product. Now we're going to do this the hard way. We're going to go through all the algebra. When we go the other way around, we'll just make some sort of hand-wavy arguments. Okay, so let's consider this now. And what we're looking at here is writing this out, but wherever we see a Z, we're going to replace that with tau of Z. And so we see that sitting here, and we see that sitting here. So if we replace, these are what's replacing the Z in the overall Blaschke product. Okay, well, now we just do some algebra. And the algebra that we're going to do, and I'd encourage you here to pause the video as you need to and just work out with pencil and paper. But we're just going to put things over a common denominator. But then we are going to also use 1 in the form of e to the I lambda over e to the I lambda to make sure that every term has an e to the I lambda that we'll be able to take out and cancel. So let's do that here. We're going to just multiply this up by this, and then an e to the I lambda over e to the I lambda. So that's going to leave these two terms. It's just the distribution of this. And then these remaining terms are going to be this product here. This times e to the I lambda over e to the I lambda. So that gives us our numerator. And then our denominator is just this. So we're all over that. Now we turn to the denominator of this. And again, we're going to put this over a common denominator. And we're going to do the same thing. So we're going to multiply by e to the I lambda over e to the I lambda when we need to, so that we have an e to the I lambda in every term. And then appropriately put over a common denominator. So as we do that, we see that the common denominator in the original numerator and the original denominator is the same, so that can cancel. And now we can cancel also an e to the I lambda everywhere. And we'll start to rewrite this out a little simplified, but we still have a few steps to go here. So now let's identify some terms are being multiplied by Z, and then some terms are constants. And the same is true down here. Here's some terms multiplied by Z, and then here are some constants. So let's collect those and distribute out the Z. So we've distributed out the Z here, and then we have just a constant. We have the constant here, and we've distributed the Z out here. Our phase factor is just coming along for the ride, and then our product of all these different factors as well. Okay, now what we're going to do here is inside here, we're going to pull out an e to the I lambda. So this will become 1. And then in doing so, then this has to be e to the I plus, or e to the plus I lambda. And the same thing is going to happen over here. We're going to pull out an e to the minus I lambda, and that will leave an e to the plus I lambda. And I want to make sure, I think I might have that should be a z bar. Okay, so now let's look at what we have. So if we inspect this and compare it to this, those are complex conjugates. See, this is complex conjugate, complex conjugate, this is complex conjugate. So let's just call this B1, and then this is going to be B1 complex conjugate. So we're going to have B1 over B1 complex conjugate here, times Z. And then let's look at this and this. We see that those are complex conjugates as well. So let's see. I think I have, yep, I made a mistake here. This A and this Z are down here. So had two mistakes there. So these are indeed complex conjugates of one another. So let's call that B2 and B2 complex conjugate. So that's being multiplied by Z. And so now we have a structure here that is a Blaschke product already, but we can clean this up a little bit more to get it to look just like this. So let's pull out a B1 here. That's going to leave a Z minus a B2 over B1. And then we're going to pull out a B1 complex conjugate here. And that's going to leave a 1 minus a B2 complex conjugate over a B1 complex conjugate. This is just a phase because it's B1 over B1 complex conjugate. So that's just something like e to the I something. So although it will depend on K, all it's going to ultimately do is contribute to the overall phase. Right? So we don't know what it is, but it'll contribute to the overall phase. So we'll just pull that out there. Cheating a little bit here, like this is indeed, these B's do have the K's in them. Each phase will be dependent on K. But once we have a fixed set of zeros, that's just an overall phase. So we are indeed in this form here. So we have shown here now explicitly, kind of the hard way, that we have the composition of a Möbius transformation followed by a Blaschke product is a Blaschke product itself. Now, we're going to now do it sort of the easy way and certainly not the rigorous way. We're just going to kind of give some motivation here for the other way around. So now we're going to take the Möbius transformation of a Blaschke product. So we know when we listed the properties of Blaschke products, you can always post Blaschke product, do any kind of a Möbius transformation to it, and you're still good. And that is the case, but let's kind of make an argument for that anyway. Well, there's going to be n zeros in D, and the modulus at the unit circle is 1. And again, as we saw, that if that's an analytic function over the whole disk and has these characters, then it must be a Blaschke product. So all we need to do then is show that after we do a Möbius transformation, we end up with these same properties. And then that's going to be our sort of proof here. Okay, so we do a Möbius transformation. That's a conformal transformation of the unit disk to the unit disk. So it's bijective, and it preserves angle. It preserves like the topology, so we're not ripping or folding over, getting ramifying 2 points. We are just one-to-one in onto the disk, and likewise, and separately, but likewise, one-to-one in onto the unit circle. So that's going to take, I shouldn't have K, I should have N here. That's going to take the N zeros to the N zeros. They'll change their position in the disk, but they'll stay in the disk. They won't go out of the disk. And it will maintain a unit modulus at the unit circle. So those satisfy the criteria. It's analytic function, has n zeros, and it is unit modulus at the unit circle. So we've taken an nth degree Blaschke product, and we return with an nth degree Blaschke product. All right, so As I said earlier, we're going to use this in several places, but most importantly in being able to normalize Blaschke product, and then we can just work with the normalized Blaschke product because we know we could take any arbitrary Blaschke product and normalize it. So we'll see you next time when we do that.